All right, so in cryptanalysis, we say that every attack starts with a distinguisher. So our aim is to find a distinguishing property in the cipher, so we can distinguish it from a random permutation. So in order to understand the statistical attacks, let's look at a very simple example, a dice example for distinguishing. Okay, so the question is very simple. You are given a dice and you are allowed to roll it to see the result as many times as you want. So you can roll as many times you want. You are asked to determine if the dice you have is a fair dice or it is a biased dice which rolls 6 with probability 1/3. So for the fair dice, this probability is 1/6. I'm assuming that dice has 6 sides, okay? Not a Dungeons and Dragons dice. So question is, what would you do? So of course, when you think about it, you can say that, okay, I can roll the dice n many times and look how many times I observe 6. So this is actually rolling it n many times means that you are turning a Bernoulli trial into binomial distribution, right? Because seeing the 6 is success and not seeing it is a failure in the Bernoulli trial here. So if you roll it n times, for the fair dice, you will expect to see n/6 many 6s. And for the biased dice, you expect to observe n/3 6s. Because in the binomial distribution, the expected value is n times p, which p is the probability of the success. So if you increase n, these expected values will be distant than each other, right? This is the good thing. So higher the n is better for the distinguisher. But increasing n, will take a lot of time. So our aim is to find an optimum value where I can distinguish it. So in this scenario, one expected value is n/3, the other one is n/6. So in the experiment you perform, if you observe any value, if you observe, so you put your threshold between n/3 and n/6. So the experimentally observed value is less than this threshold, then you say that it is a fair dice. If it is larger than that, you say that it is a biased dice. But sometimes you make a mistake, right? Because it might be fair, but just by chance you roll too many 6s. So it will be higher than the threshold. You will say that this is biased, but in reality it is fair. So this is false alarm. The other way around is non-detection. So question is, what will be the probabilities of these scenarios? So we actually can write it as a binomial distribution, choose an n, and then calculate the probabilities of non-detection and false alarm probabilities, okay? So we will see them when we calculate data complexity or success probability of a statistical attack. But before that, we have to see how this idea actually applies, right? Because in statistical attacks, our aim is to find such a distinguishing property, which is an event that happens with different probability for the cipher and with different probability for a random permutation. All right. With this basic example, let's look at the non-generic attacks and see what are the main ideas behind them. So many cryptanalysis techniques are statistical attacks, like differential cryptanalysis, linear cryptanalysis. Statistical attacks first discover a property of R runs of a cipher, which happens with probability P0 for the cipher and probability P for a random permutation. So in our dice example, P was 1/6 and P0 was 1/3. Such a statistical property is referred to as distinguisher. A distinguisher can be used to distinguish R runs of the cipher from a random permutation, because this property, is an event on the R runs of the cipher. An attacker can then add R1 runs to the top or bottom of this distinguisher to attack R plus R1 runs of the cipher. Okay. So if a cipher is 10 runs, and if you find a distinguisher for 8 runs, then by adding 2 runs, you try to capture the round keys of those 2 runs. Okay. If you can capture it, then you break the system. So an attacker can add R1 runs to the top or the bottom of this distinguisher to attack R plus R1 runs of the cipher, and this is how it works. So your aim is to attack R plus R1 runs, right? So you capture or gather somehow n many plain text ciphertext pairs where plain text ciphertext is obtained from this plain text. With the secret key, you don't know, but you use the secret key to encrypt this plain text for R plus R1 rounds. Don't forget that we cannot see intermediate values. We can only see the input and output. Okay. Next aim is to try every possible key that are used in the added R1 runs and count how many times the distinguisher is observed. So you might say that, okay, this is very similar to exhaustive search, but here not every round key bit is used. So we are actually in this scenario try to guess just a few rounds of the round key. Sorry, few bits of the round key. Wrong keys are assumed to act like a random permutation. Okay, here actually the distinguisher comes into play. Now, because my aim is to distinguish the correct key from the wrong keys. In the distinguishing attack, recall that I was trying to distinguish the cipher from a random permutation. So there was one correct and one wrong answer. Like in the R dice example, there was one fair dice and one correct dice. I was trying to guess which one is mine. But when I try to capture the secret key, there will be a single correct key and many wrong keys. So I have to distinguish one binomial distribution with many other wrong binomial distributions. So it is a little bit different. So I may need to make an assumption here, and the assumption is that I assume that wrong keys act like a random permutation. And this is known as wrong key randomization hypothesis. It is not correct, but it works. Okay, this is the catch. So if you look at them as binomial distributions, expected value of counters are n times p0 for the correct key and n times p for all of the wrong keys. So here by wrong keys and correct keys, if I'm trying to guess like 10 bits of these added R1 rounds, there is one correct key, but there is 2 to the 10 minus 1 wrong keys. So these are the binomial distributions I'm trying to distinguish. So whenever I observe this event, I increment the counter for that key, right, as I did here. By looking at these counters, we can capture the key material of the R1 rounds. That is the idea. Remaining key material can be captured by exhaustive search. Since now the remaining bits are smaller, I can perform an exhaustive search, or I can perform a similar attack with a different distinguisher if I can find one. So this actually explains, these 6 steps explains almost every cryptanalysis attack. So you can see it as a pseudocode, but in practice, of course, you need to do many tricks in all of them. So idea is simple, but in practice, it needs expertise to use it. So non-generic attacks. Exhaustive search provides an upper bound for security, right? You cannot have more than k-bit security for a k-bit block cipher. Okay. If the attacker captures 2 to the b minus 2 known plaintext, so everything except 2 plaintext, if I capture them and no corresponding ciphertext, then the cipher should still be secure, so that the attacker should be unable to distinguish the 2 remaining plaintext and ciphertext. So you can randomly guess. Your winning probability will be 1/2, but you shouldn't have any more advantage than that. If you can guess with 1/2 plus epsilon probability, where epsilon is your advantage, then this would mean that the cipher is not that secure. So I'm really expecting a very good security. So any attack that requires less time than exhaustive search, less data and memory than the table attack is considered as the cryptanalysis of the cipher. If the attack requires resources that are not practical, for example, 2 to the 80 terabytes of storage, which we don't have, then we call that this attack is an academic break, but not a practical break, because I cannot apply it in practice. So there are some theoretical attacks for AES, but they're not practical. This is why we are still using AES. Okay. So there are many non-generic attack techniques. Differential cryptanalysis is one of the first academically explained attack. Then people added many variants to it. One famous one is impossible differential cryptanalysis, looking at the problem in a very different way, but it works very nicely in some designs. There's also linear cryptanalysis, but of course you can, have multiple linear paths or multi-dimensional linear paths. So there are also many variants of linear cryptanalysis. Actually, you can combine both and perform differential linear attack. But there are many other attacks. Some of them are algebraic attacks like integral cryptanalysis, extended sparse linearization, or people keep coming up with new attacks like invariant subspace attacks from 2011 or subspace trail attack from 2016. So whenever somebody finds a new cryptanalysis technique, actually you need to go back and check if all of the ciphers we are using is secure against this kind of attack. Okay. And in order to come up with new techniques, it is always a nice idea to attack lightweight designs because they are so lightweight, you can come up with new designs. It is easier to analyze. And many techniques are actually found by analyzing ciphers like present and so on. So let me briefly explain what linear cryptanalysis is, the main idea behind it. So it was discovered by Matsui around 1992. This is the first experimental cryptanalysis of DES. So he chooses a secret key, encrypts many plain text with that secret key, and obtains the ciphertext. So he somehow forgets the secret key, but he has many plain text and ciphertext. Just by looking the relation between them, he recaptures the secret key. So he experimentally performs this attack, but data gathering in this attack in practice can be impractical because he actually uses every computer in Mitsubishi where he works at the time and does this attack. But in practice, you need a lot of data. So the idea is as simple. Check the relation of inputs and outputs as a masking here. So P is your plain text block, C is your ciphertext block. And here I'm performing an actually masking operation where I'm multiplying A with P. Here actually I'm multiplying A and P bit by bit, and then I XOR them. Okay, I do the similar thing with C. So choosing of A and B actually the distinguisher you find actually. So at the end, since you are XORing everything, the result will be either 0 or 1. So in a random permutation, the result should be 0 with probability 1/2 and 1 with probability 1/2. But if there is a weakness that you can find, this result gives you 0 with probability 1/2 plus or minus some epsilon. So if that epsilon is bigger, it is better for the attacker. So you can break the system. So this is your distinguisher. So for example, consider the XOR of the least significant bits of the plain text and the ciphertext in the XOR P0, C0, right? It should be equal to 0 with probability 1/2. A high bias from 1/2 can be used as a distinguisher. So that bias actually will be your advantage. Differential cryptanalysis is different. So let me go back. Here I have the plain text block and the ciphertext block, right? This is why it is a non-plain text attack. I'm not interested in the structure of the plain text or the ciphertext. So if I need 1,000 plain text to perform an attack, I only ask you to give me 1,000 plain text and corresponding ciphertext. I don't, introduce any condition on the plain text or the ciphertext. But in the differential cryptanalysis, I need something more. So the first public announcement by Biham and Shamir around early 1980s, we already talked about this. Agencies knew it even back in the Second World War. So yes, first discovery may be as early as the Second World War. Aim is to find the paths, which we call sometimes differential, but in the classical differential cryptanalysis, we call them characteristic, so that when the input difference is alpha, so by input difference, I have two plain texts, but their XOR is alpha, so I'm fixing this. This is the distinguisher I have, because for this input difference, after R rounds of encryption, output difference is beta with probability P0, and we want this P0 to be, high, so that we can distinguish it. So this is the distinguisher you use, but as you can see, I need pairs now. And their XOR should be in specific format. This is why I call it a chosen plain text attack. Okay? That is the difference. This is strangely resistant to differential cryptanalysis. So to break the whole DES, 16 rounds, you need around 2 to the 49 chosen plain text. So this is important because when Biham and Shamir discovered differential cryptanalysis, They actually applied these techniques to some of the known ciphers around that time, and they break some of them. In those attacks, they needed like a few thousand chosen plain text or something. So until the cryptanalysis of this, people never used actually 2 to the something notation, because generally you needed a few thousand, a few hundred plain text. Now they realized that the cipher is strangely resistant. They wanted to, push the limits and check if they still break the whole cipher, but using many data. And they realized that they need around 2 to the 49 chosen plain text. As we talked about before, this is resistant to differential cryptanalysis, because when IBM designed it, they didn't know differential cryptanalysis. They chose bad S boxes, but NSA interjected and changed the S boxes and made it resistant against differential cryptanalysis. Because they knew the technique of differential cryptanalysis at the time, around 1970s. So they didn't want other countries to listen to their communication when they used this. So NSA made something good by, changing the S boxes, by giving good S boxes. But what they did was to, reduce the key size to 56 bits. So they also make the cipher weak against people who have huge computational power. And at that time they had supercomputers, so this is why they make it, weak. So this is why they could actually listen to those communications, because they have best supercomputers of that time.